Hi everyone, happy evening. Welcome. Yeah, let's give folks another minute, then we'll start. All right, I guess we can get started while still waiting for some other folks to join. Today's topic is about tools. As you know, in FL competition, we're not just gonna drive a driving base around the mission table, right? We're gonna have the base to do something. And in order to achieve that, we need to come up with some ideas for the tools. In the previous session, we talked about some of the simple tools, right? Like a pusher, like a grabber, right? And potentially a lifter. Hopefully um, you have seen some of those tools. And today we're gonna talk about how we're gonna bring this tool to life through some word block coding in Spike Prime. All right. So let me bring up this module and we'll talk about some of these topics. Give me 1 second. Okay, so this is a tutorial. You also have access from your Spike program software. Just go down to the bottom, number 7, time for upgrade. Now you have the driving base, right? And you have the foundation of coding. Now think about we have the mission models we'll be building, right? Coming Wednesday. And given a problem we're gonna solve, which we do not know yet, we need to design different tools, right? This is the module to help get us started. So there's a video. Let's take a watch together. Right. So can someone tell me in this video, what is the task we're trying to complete? Let me just stop at this specific screen, so you can try to think about it. How do you describe the task we're trying to complete? Ethan, want to give a try?
Yeah, basically like just to like release the like thing and then raise it with the hooker thing.
Mm-hmm. So you have this hook, or you call it a lift, right? You move towards this. You can call it a crate. It's a simplified crate. Is a like a box you store things, right? It's just one side of it. So you move forward, go through that crate, right? And then you bring it up. Take a look, right? And then you bring the bag, right? And then potentially you drop it to the base or drop it at a target place, right? So this is a simple task that can be completed using a tool um, like the lifter, right? Okay. So in the uh, season competition, um, you know, when it comes to the time we will review the mission sets or the list of missions, we're gonna be going through this process, right? What is the problem we're trying to solve? Like in this case is to bring a crate back, and what is the tool we need to design to solve it, right? And how we can code it out to control the tool. Okay, very good answer. Thank you, Ethan. Now let's think about another question, right? So in this model, right, everything come from the same tutorial, so you have access. If you want, you can even bring up the software and follow me, all right? In this picture, how many tools do you see? You are familiar with the basic driving base. Now you see something additional. What are the things you see additional? Can I have another person to answer this question? You have something in the back. What is this called? I don't see people raise their hands, so I may just ask someone. Next in line. Audrey, you are the next person after Ethan. Do you have a quick answer?
It pushes stuff.
The question is, what other tools do you see from this design?
Like a blade that like pushes things.
Mm-hmm. Dozer blade, right? So that is the one on the top, right? With two arcs and a bar, right? You can think about the dozer blade can go up and down, and it can just stay in place and move with the base to push things and grab things. Very good. Thank you, Audrey. What is the other tool? The lift arm, right? Ethan already mentioned. So that thing goes through some object with a hole in it, right? Or with an opener in it, so that can go through and then it can lift up and drop down, right? And to it can carry things around after you grab it through the arm. All right. So these are the two very simple tools we can easily build, right? Think about how you're gonna build it. Can someone give a guess how many pieces you need to build the dozer blade? Just give a rough estimate. 10 pieces, 5 pieces, Ethan?
Like 10 to 15 pieces, maybe
How about the lift arm?
like 10-ish.
Okay, the same. Okay, let's see the answer. All right. 26 steps. Sounds like more than 10 pieces. Do you agree? Maybe not. Maybe not. Each step may, yeah, I would believe 20 more pieces because each step is more like a piece add-on, right? So maybe it's just a little bit more than we think, but good guess. No worries, right? So why ask these questions? Because you need to be able to quickly narrow down to how complicated something is. All right. So when you look at this picture, right, you know, oh, there's something called a dozer blade, but I have no idea how quickly I can build it. Or if I need to change the design, how complicated it's gonna be. Now we have an idea. The dozer blade actually, based on this design, required 26 steps. So more likely involving 26 pieces, right? Same for the lift arm. You know, you can see this is a very fine design with lots of pieces in it. But of course, we can give a try to see if we can simplify the design, right? But that will be another story. So what are these crates? These crates are the objects you can test your tools, like the blade and the arm, right? So the arm is gonna go through these holes, bring it up and bring it back. Then the blade is gonna use the bar, like your bumper bar on a car, right, to push it. Okay, that's why it's called a dozer blade. It's like a bulldozer. Very good. Good try, Ethan. All right. So now let's take a look at this code. We're gonna run through this very quickly, right? And then we're gonna talk about something more like thought-provoking, all right? So this is the program that will help us to do something. And I will tell you, this is to program this lift arm, right? As you see from the video, the lift arm going through a crate, lift it up and bring it back. All right. This is exactly how it can get the job done. Can we have a volunteer to walk us through the code and tell us what are the few steps, right? You describe it in plain language, what the lift arm is supposed to do, and how that got translated into this block code. I have the next person in line, or we have a volunteer. Again, the question is, what are the steps to move a crate, right? Go through the hole, lift it up, bring it back, and how that um, how those steps translated into this code. Okay, I'm just gonna give a try for the next person in line. Natalie, are you there? Do you want to give a shot?
Sure. You set motor speed to 100, and then you turn it counterclockwise for 1 second, and then you turn it clockwise for 70 degrees,
Mhm.
and then you for play beep for 60, and you play it for 0.2 seconds, and
Mhm.
then you set motor D to run clockwise for 180 degrees.
Very good. You just walk us through the code. Very clear, very easy to understand. But before we do that, can you describe what are we supposed to do when there's a task to bring a crate back? So now you have the lift arm, right? Your teammate Audrey built it for you. All right. Now you're the coder. Put your in that hat, right? Um, you're gonna translate the action of the tool, which is the lift arm, into the code. So what are the actions that lift arm is supposed to take? So think about visualize it, right? We don't see the crate here, but think about visualize it. There's a crate in front of the lift, about maybe 10 inches away. What is step 1, step 2, step 3? Okay, I'm gonna ask, you wanna give a try first, Natalie? Yeah.
Okay. The arm goes down, and then it lifts the marker up, and then I think it lifts it down again. Wait, no. I think it lifts it up more.
Very close. You bring the arm down. That's very good. What is that called? Do you know? There's a term for that. Reset. All right. So this is a very important concept. I want everyone to see this. Reset. Why you need to reset? Because you always want to start from the original default position. Any of you do sports? Let's expand this a little bit. Ethan, where do you start when you play tennis? Where is your hand? Left hand.
In front of you?
In front of you, of course. But I can put the hand in front of my head or in front of my belly button. What is your left, when you are receiving the ball, where's your left hand on the racket?
Like the bottom-ish?
The choke, right?
Yeah, oh, my left hand, yeah.
Yeah, okay.
Right hand
The
though.
choke. Yeah. I know what you're talking about, but you need to see the concept, right? The choke. So when you play tennis, when you're receiving the shot or the ball, you always put your left hand on a choke to make sure you are ready to hit with your forehand or something, right? Or your left hand is putting somewhere else if you are more familiar with that position. But you always start from the same position because that help you to react to different scenarios, right? That help you to think about, how to be consistent, right? What is another example? Any other person doing sports on the call? How about Yolanda? When you play golf, what is your fixed position for something? Starting position.
You have to hold your arms out straight.
Yeah, hold your arm out straight, right? Like a
Yeah.
V shape or something. Yeah. And you need to look at your ball, right? Or something like that.
Yeah, the whole time.
What's that?
You have to look at the ball the whole time.
Look at the ball the whole time, even, after you swing, right?
Yeah.
Perfect. Yeah, thank you. You just give a free, lesson on, the best posture for hitting a ball. Great. Yeah, so everything has a starting position that help you to get settled, always be consistent and so on. This is same thing, right? We went a little bit far, but we will come back. So starting position is to keep the lift arm low, right? Because if you keep it high and you want to adjust it, you don't know, turn it higher by 5 degree or 10 degree, right? You don't know because you don't know where the position is. So by keeping the node, you know, you start from maybe 0 degree, right? And then you can do counterclockwise 70 degree, you know where it will be positioned at that point. Okay. So starting from the lifting position being low, and then that's the step 1 called reset. The second step is going forward, right? I think Audrey, Natalie just mentioned, like, right? You need to push the wheels forward to get closer to the object. And ideally, you need to go through that. Let me just put it here. You can think about it, right? Ideally, you need to go through that little hole. How do you go through that little hole? So step 1 is to reset, lift the brain down. Step 2 is to move towards the object. What is step 3? Isabel and Aiden. Oh, sorry, actually, Vivian is the next one in line.
Vivian went to another class.
Okay, no problem.
Available.
Oh, sounds good. Yeah. You know, we can prompt her after she returns. Thanks for letting me know. Is Isabel or Aiden here?
Hi. Hi.
Hi.
Hi.
Hi.
Did you hear the question?
What?
No.
The question is, okay, you have this arm, lift arm. You lower it to the level of the crate. You see my screen, right?
Yeah.
Then move towards that crate. That's step 2. What is step 3?
Lift it up.
Lift up. Okay. So how do you know when to lift it up? If you move like 1 inch, but that crate is 10 inches away, how do you know when should you lift it up?
After you hit something.
Motions.
What is the sensor you're gonna use?
Motion.
No. No, that's not even a. Wait, distance?
Yeah, distance. Good. Very good job. Okay. Distance sensor. So you're gonna keep going forward until you are reaching an object with a distance of
Is it still us? No.
maybe 1, right? 1 inch or half an inch, something like that, right?
Yeah.
Presumably there should be no obstacles in between, right? There's only one object towards the direction. And then when you get very close, right, you stop. And then what is step 4? So when you stop, it's like half an inch towards the crate. Can you just raise the arm? No, right? So you need to calculate, you know, how much more you're gonna go. Maybe you're gonna go an extra inch, right? So that arm is going through that little hole of that crate, right? And then you are sure you now raise it, it can be picked up. All right. So that is how you hook everything up, right? So first you lower the lift down, you move forward, you use the distance sensor to get very close. Now you move a little bit more to penetrate, right? And then you lift the arm and then you drive back. Does that make sense? Okay, so these are the different steps we're gonna implement when we complete the mission. But as you know, you already talked it out, so it's not that really hard, right? Once you know how to do it. Now back to this code. Um, I think Natalie just walked that through, right? So can anyone tell us how to understand this piece? Like the motor D, which is the one controlling the arm, right? Going counterclockwise for 1 second, and it will lift it. How does that make sense to you? Why is not up and down? Why is like counterclockwise, clockwise? Somebody has his hand up. Ethan, you want to give a try?
Yeah.
Sure.
So because like the motors don't have like an up and down motor, it's a like spinning motor.
Mm-hmm.
And counterclockwise, it can only go counterclockwise and clockwise.
Exactly. So let's I don't know if you guys remember, all right? So on the main base, there's like 6 holes, right? The 6 holes are the ports that you can hook up the motors. The holes can only spin forward or backward, or in other words, counterclockwise and clockwise. In order to raise this arm, you have to use the turn, right? But you're gonna translate that turn through this gear into a momentum going up and momentum going down. All right, so it's a 2-step there. It's not like a 1-step. All right. So this is a very important to understand, and otherwise you may be puzzled why it's like counterclockwise, clockwise. The motor, oh sorry, the lift arm is going up and down, right? There's no like a counter direction. All right. So basically, this is a very simple program just to lift up and bring down the lift arm. It does not drive the base, as you can tell. So it does not really get the job done if we want to bring the crate back. All right. But once it comes to the real mission, we'll make it for real. Does anyone have any questions about this piece of code block? Okay, good. All right, so this is pretty much it about this tutorial. Now I'm gonna ask you some prompting questions for you to think about. How do you come up with different tools to solve different problems? All right, so I want everyone to try to give your answer if you can. All right. Why are the tools useful in the competition? I think I already explained that, but yeah, can you use your own words and tell everyone, tell the judge? Ethan?
The tools help you do different missions.
Mm-hmm. Can you be more specific? If you explain to a judge, the tool help me to do different missions, maybe you will get some credit, but not all the credits, right?
Like, basically, for example, the like arm can help you like pull something up, and then the dozer blade, for example, can push or pull something.
Exactly. So a tool can help us to get a specific job done, right? Based on what action we need to take using the tool, right? Something like that, like lifting, grabbing, pushing, moving things, right? Or in other words, if you just have a base, you can only drive around, right? You cannot really do things like lifting because you don't have an arm. You cannot grab things because you don't have a hand or something, right? So those are the things. Ethan, you did a very good job. You know, if you add a little bit more details, then the judge will understand. Oh, we truly understand why we're supposed to do certain things in certain way. Great. Now everybody knows why we need tools, right? Tools are must have. Tools are critical important for our success. We need to be very creative in terms of designing different tools and work with others on the team to get them implemented through block coding. All right. Second question. I want you to think about why do teams often change tools during each competition run? Why do you need to change tools? I want to have another person to answer this question this time.
To complete different missions?
Yeah, there are different missions, and then
You need different tools to complete them?
exactly, very good answer, right? Can you use what is a good example in life? You cannot use a tool to do everything, or it'd be weird to use a tool to do something. Can you use a spoon to cut wood? Right?
No.
Can you use a hammer to eat cereal? Right?
No.
Yeah. So, but don't use that example in front of a judge, right? That's kind of not appropriate. So, but those are the things you can think about, right? It doesn't mean like you have a tool, you have to use it. No. We need to think about the goal, right? I think in the first class, we talk about what is the goal we're trying to achieve. That is the starting of the problem solving. We always think with the end in mind, right? What is the goal we're trying to achieve, right? What is the mission? What is the problem? Then we think about what is the right tool. Maybe we have all the tools in our toolbox, but we need to pick the right one, right? If the last round we use a tool A that cannot be used to complete in the next mission, we need to swipe it up for tool B, right? So those are the thought process. That is why we need to change tools. Very good answer. Thank you, Aiden. All right. Third question, I think we already gave the answer in the last part. That is why we need to reset position, right? The answer is you always want to start from some default position so you can be consistent, you know where you're going. And the program, the steps to solve the problem is more repeatable, right? If you don't start with the same position, you are likely to go too far or you are likely to go not far enough, right? And you are likely to miss the target, which is not what we want. Good. The last question I want you to think about is when you design a tool, how do you tell if the tool is good or not? How do you tell if the tool is good or not? I have another person who have not answered the last two questions. How about Natalie?
You test it and see if it's like stable.
Mm-hmm. If it's stable, or in other words, sturdy, right? I think by stable you mean sturdy, with enough strength. Is that what you mean? Strong enough?
Yes.
Okay, yeah, that's very important. So for some of the missions, you're likely to lift something, for example, right? Is the arm easily break or change position, right? Do you have a limping arm, like arm, right? So that is the strength characteristics of your tool. You want to make sure your tool is strong enough. That's very important. Or in other words, stable enough. Good. What else? Yolanda, do you want to give a try? Besides the strengths, what other characteristics you need to think about when designing a good tool?
Maybe like how it's gonna work.
How it's gonna work? Very good. You're actually right. Yeah, you answer the question using your own language, right? So it's the design, right? There are many lift arms you can build. There are many different type of dozer blade you can design, right? So how do you know you come up with a good design? to get the job done.
Um,
Talk about strengths. Minus that, we don't need strengths anymore. We need to have a strong enough tool. But other than that,
I don't know.
yeah, let me give you a hint. So you're likely not to gonna use only one tool to complete all the missions. You are
Mhm.
likely to swipe in and out different tools. How do you measure? How do you measure? That is, how do you tell it is easy to put on and take off a tool?
Maybe there's like a slot that you have to insert the tool into.
Yeah. And that need to be easily,
Easily taken off and taken and put on.
exactly. So it's easier to kind of swipe in and out, right? That is
Yeah.
important design aspect of the tool. Very good. Yeah. So a good tool need to be easily swipe in and out. Even there's a tool without using, I know in Lego there's like a clipper thing. I don't know what it's called. Ethan, do you know what I'm talking about? Sometimes you cannot take out a piece. You have to use that tool. Yeah. Plier.
Oh, the piece remover?
Yeah, piece remover. Thank you. If you implement a tool, design a tool without a piece remover, you cannot take it out. It likely not a very good design, right? Okay. What are other things? We still have like many other things we will be going through, as we go. But another characteristic is also a very important consideration. Did I ask Audrey? You want to give a try? What are other aspects of the tool we need to think about when it comes to a good design, a good tool?
Like how efficient it is, like if it's the easiest way to like do something.
Very good. How efficient it is. If a tool can get 3 missions completed in 1 run, is it gonna be more efficient than another tool that can only complete 1 mission at a time? Yes, right? Because you save time for the trip. And if a tool, think about the other side, right? If a tool can complete as many missions as possible, do you think this tool will be big or small? A multitasking tool is likely to be big, right? Or you finish like very similar tasks. You could use the same tool, but very likely the more task you target, the more complicated the tool is gonna be, right? So what is the downside, or what is the risk of using a very complicated tool? Ethan, you want to give a try?
Like it could have a chance of failing because it's so like complicated.
Yeah, more specific. Why it can fail?
Because like so many things are like in like the main thing. Like so much things are happening at once. Like it's confusing.
Yeah, it's confusing. Exactly. So something like you can get snagged into something because it's too bulky, right? Or the tool is hard to move because it's heavy, right? Or the tool is just more complicated to operate, so it's more likely to snag into something or fail to execute the task. Yeah, very good. So you don't want the tool to be overly complicated. Although we need to have a tool that can get as many done as possible or as much done as possible, but we don't want to overcomplicate design because that is kind of defeating the purpose, right? And in relation to that, when we design a tool, right? We need to make sure it's strong enough, it's stable, right? It's sturdy, and it has a good design, can be easily put on and off. It's very efficient, right? Everything you have just talked about, make sure we have a rubrics to score each tool, right? We may come up with different designs for each tool and we can score it, right? Strengths, 5 out of 5. Design, 4 out of 5. Multitasking, 3 out of 5, things like that. Then we can rank these tools and pick the best one, right? That is an exercise we can do when it comes to real work. Another dimension we can score a tool is procedure, right? We want to make sure the tool can be accurate, right? Can reach exactly the distance we want it to reach to, right? Can lift, right, as much as we want it at a certain angle or certain distance. So those are the metrics we want to make sure we can track as well, to make sure the tool is precise enough to use for our purpose. All right, good. So we have gone through all these design questions about how to design a tool. And then next, I'm gonna just show you a video. Someone else designed a simple tool and involve it into something more complicated over time. And I would like you to think about how you can come up with this progression or incremental approach, right? And give me a minute, I'm trying to find the video. Okay, I got it. Let me share my screen again. Oh, am I still sharing my screen? Maybe not.
You
Yes.
are.
I am, thank you. Okay. So this is a video showing the progression of a grabber, right? Grabber is you reach to something, you bring it back. It's a grabber, right? And I want you to think about how it evolves from a very simple tool to a very advanced tool. All right.
Picture this, saving the
On the commercials. Any reactions to this video? Do you like the tools it built?
Yes.
Yeah. And how do you think this person can involve this grabber tool from a very simple and basic
10%.
version to the last version? What is his thought process. For example, the first task is to just grab this plastic square, right? It's laying flat on the ground. Then if you move a grab forward, you have something to latch on it, you can just return. It will automatically brought back, right? Yeah. Then the second one, it have, what is this mechanism? Anyone? What is this vertical black bar that can go up and down like a lock? Locking, right? So basically, you can only go in, you cannot go out. Why do we need this design for this type of object, which is rubber band type of thing, right? Ethan, do you have any ideas why do we need a locking mechanism for this?
So like you can like drag it away just by like driving to it
Yeah, yeah.
or like a task or something.
Mm-hmm. And if you don't have this, the rubber band will slip out, right? Because it's so light and slippery. So having this, you can drag it. Exactly. Okay, so the third one, let's take a look, right? So it's kind of, saving a wild animal, right? There's an injured animal. You try to bring it into the crate and ship it with a car, something like that. But this animal is just sitting there, right? It's not moving. So in order to be able to lock the animal in, it also implemented this locking mechanism. But in this case, it has two bars. Why it has two bars in the one bar? Aiden? Why you need the two bars here to lock the animal? Oh, maybe Aiden's not there. How about Yolanda?
What?
Why do you need the two bars here to lock the animal in it?
Oh, maybe because like if you like move it back, it might like slide out.
Exactly. Because the animal is not big enough, right? To be locked in using only one bar. Very good. Very good. And the third advancement is this push mechanism, right? When you push this one like arm, I would say, right? It kind of push a horizontal bar back. It's more like a lever. It bring this lever back and then it drop the pin. Do you see that?
Yes.
Why this mechanism is needed for bring back this tire?
Maybe because that round thing, and then when it releases, it just the tin round thing, it pulls the tire back.
Mm-hmm. So what is the best way to grab a tire? Do you want to grab on its ring, which is the black rubber, or you want to grab it inside the hub and spokes?
Probably the outside, the rubber.
The rubber. Okay. When you grab the rubber, you are just touching the surface, right? And when you bring it back, it does not actually hold on to the tire.
Oh, because it's slippery.
Yeah.
Oh, got it.
Yeah, that's okay. So that is the thought process, right? We first try grabbing on the rubber. Maybe we tried it, or it's slippery, right? And then it's not working as what we want, how we want it. Then we try to move in, right? So we use a finger sticking to the inside of the tire and we bring it back. It's not slippery anymore, right? So that is how we come up with the design. Then in order to achieve that, this mechanism help us to first raise the vertical pin high so you can get over the rim of the tire into the hub and spokes, right? And then you need to drop it so that it goes down, just like your finger pointing down, right? And then after you return, it goes back with you. So this is the how we come up with this design by looking at how we're going to solve this problem, right? For bringing back this tire. Okay, this last mechanism, can we have maybe Natalie to think about, how this is used to solve this specific problem? So the goal is to grab I don't know what it's called, maybe a block or cylinder, right? And did you notice what is the locking mechanism? Natalie, do you want to give a shot?
Maybe it was the rubber bands.
Yeah, maybe there's a rubber band, but can you tell us what is changing here before and after it grabs or it push against the wall? Like, let me show you again. Yeah, maybe it's too fast. Actually, pay attention to the left side of this grabber. This gray piece on the left is actually went inside a little bit. So this circle thing, when it touch the wall, it actually release a lock so that this left grabber hand will become smaller or will move towards the inside. This is how you can kind of clutch the two sides to be able to grab the object firmly. All right. So this is a very good answer. Thank you, Natalie. There's another design that we can think about for this specific object, right? How can you make sure you get around that object and then firmly lock it before you bring it back? Very good. Any other questions for anything that we have watched from this video? Good. Alrighty, let's take a look at some of the designs other people did. Let me see if I have some good material here. No, I don't think this is a good one. Give me a second. Okay. Yeah, I don't want to boil the ocean, so definitely don't expect you to remember all of this, and you will come up with more creative design to to be smart about solving problems, right? But here just some of the ideas other people come up with. This is from a kind of online tutorial for the potential types of attachment or tools FL team may come up with to solve their problems. Before you design a tool, you need to think about what the tool is going to do, right? Normally it involves this type of actions: pushing, pulling, lifting, dropping, dumping, placing, delivering, releasing, capturing, right? Shooting, all that. I don't think we'll encounter any shooting, but those are probably more advanced actions. Then this is some of the inputs to your tool to make it behave differently. And then these are some of the example tools and how they can be simply built, right? For example, we look at the dozer blade. It's kind of a pusher and a grabber together, right? So this is also another design. It's much simpler. So we can come up with a simpler design if we can. So there are really no set rules for it, right? And this is a hooker. For example, you can use a lift arm to bring the back, or you can use a hooker. Maybe the lift arm during transportation, it can slip off, right? If you don't have a locking mechanism. But this hooker will make sure it grabs it firmly because it's actually push the object against itself, right? So that it's not gonna easily slip. This is a fork. What does a fork do? A fork has multiple prongs to capturing objects. So some of the objects may be, you may have multiple objects, right? You may need more than one arm to capture each one of them. So this is not a consideration. This is a dumper. This is a guide. Guide is more like a tool. You can make sure, oh, I'm leaning towards a wall because the barrel, right? In the last video, we saw the barrel against the wall. So if you want to be consistent every time, you want to make sure you reach the wall before you take action, right? So this guide is actually helping you to stay on the wall, right? Before you reach the barrel, and then you can do something at your desired position, something like that. Okay, so yeah, I will save this to our team folder, and you can refer to it in the future if you need it. Alrighty. I think we are done for this tutorial. We covered everything. Does anyone have any questions or comments based on what we have discussed today? Again, just to recap, today we talk about tools. Using tools is an upgrade of what we have learned. Right? You have the the driving base. Then you build different tools that can be attached to driving base. That is how we can get down or we can complete the mission challenges. And when we meet in the next few weeks, we will be working together on some of the sample code, and hopefully we'll be able to have the opportunity to test our tools, right, to make sure the code gets what we want to do with the tools. And it will give us a good jump start before we tackle each actual challenge in the missions. All right. With that, I want to thank everyone for your joining and your active participation in the answering the questions. I really appreciate it. I hope it helps you to learn as well. With that, I will see you next time.
Bye.
Thank you.
Okay, thanks everyone. Have a good evening. Bye-bye.